object in the sky, the very source of all life and warmth on our planet, is a lie. Everything you have been told, everything you have drawn since childhood, and every photograph that has been filtered for dramatic effect has perpetuated a colossal, cosmological deception. The star we call the Sun is not yellow. It has never been yellow. In fact, if you were to stand outside Earth's protective, blue-tinted atmosphere, looking back at our star, you would be confronted with a blinding, terrifying, and utterly pure white light. That familiar, friendly yellow orb we see every day is nothing more than a trick of the light, a beautiful, persistent illusion created by the very air we breathe. Imagine the feeling of a sudden, powerful acceleration. The G-forces press you back into your seat as the atmosphere begins to thin beneath us, turning from that familiar, soft blue to a deepening, velvety indigo. We are leaving the protective bubble of home, and with every kilometer we climb, the entire nature of reality begins to shift. Come with me now, and let us embark on a journey not of distance, but of perception. Our destination is the truth of our own star, a truth that is hidden in plain sight, veiled by the very air that sustains us. You have spent your entire life under the gaze of a star that appears to be a gentle, buttery yellow. This is the color of warmth, of harvest, of the life-giving energy that fuels our world. But what if I told you that the light striking your retina right now is a composite, a filtered remnant of a much more violent, much more spectacular, and much stranger source? We are crossing the Kármán line now, the internationally recognized boundary of space, about 100 kilometers above the surface. Look back at the Earth. Notice that impossibly thin, fragile layer of gas clinging to the curve of the planet. That is the veil, the cosmic filter responsible for one of the greatest visual misconceptions in human history. As we move further out, that yellow hue fades dramatically. The light from the Sun, which now dominates the viewport, is shifting. It is becoming harder, brighter, and more intense. It is pure, unfiltered starlight, and it is overwhelmingly white. Why the change? What strange cosmic mechanism is at play to transform a brilliant white light into a soft yellow ball every single day for every person on Earth? This is where our first stop, our first module of curiosity, begins. It is a deceptively simple phenomenon known as scattering. Think about light for a moment. It is not just one color, is it? It is a spectrum, a rainbow of wavelengths, from the short, tight waves of violet and blue, all the way up to the long, lazy waves of red. All these colors are traveling together, side by side, from the Sun to your eye. Now, let us introduce the Earth's atmosphere into the equation. It is not empty space. It is packed with tiny, invisible particles, nitrogen and oxygen molecules, dust, and microscopic water vapor. These particles are much, much smaller than the wavelength of light itself, but they are absolutely critical to our perception of color. As the Sun's light slams into our atmosphere at the speed of light, it begins a chaotic, microscopic dance. The light waves hit these tiny air molecules. But here is the crucial, counterintuitive part. Not all colors are scattered equally. The shorter, more energetic wavelengths, the blue and violet end of the spectrum, are scattered far more effectively by these tiny molecules than the longer, less energetic red and yellow waves. This is a principle known as Rayleigh scattering, named after the British physicist who first described it in the late 1800s. Imagine trying to navigate a dense crowd. The smallest, quickest people, the blue light, are bounced off in every direction, ricocheting off every obstacle. The larger, slower individuals, the red light, can push their way through the crowd with less interruption, traveling in a more direct line. So, what is the result of all this blue and violet light being scattered? It is diffused across the entire sky. This is the simple, profound reason why the sky is blue. When you look up at a daytime sky, you are not looking at the sun's direct light. You are looking at the scattered blue light that has been redirected from every corner of the upper atmosphere and into your eyes. But what does this scattering mean for the sun itself? If the blue light is being scattered away from the direct line of sight between the sun and your eye, what is left? The longer wavelengths. The yellows, the oranges, and the reds. The sun's original, pure white light, which is the combination of all visible colors, has been subtly but significantly filtered. A portion of its blue content has been systematically removed and spread across the heavens. The remaining light, the light that actually makes it through the atmospheric gauntlet and strikes your eye, is subtly shifted toward the yellow end of the spectrum. It is an illusion of subtraction. The sun appears yellow because its blue has been stolen by the sky. Now I know what you are thinking. Why then does the sun look even more intensely red and orange at sunrise and sunset? This is our second curiosity module, and it is a beautiful final act of the same scattering mechanism. When the sun is high overhead, its light has to pass through a relatively thin slice of atmosphere to reach you. The scattering is minimal, and the sun still appears closer to white, though still tinged with yellow due to the small amount of blue removed. But at dawn or dusk, the sun is low on the horizon. Its light must now travel a dramatically longer path through the densest, thickest part of the atmosphere. It is like looking through 1,000 kilometers of dense fog instead of just a few. The light is forced to interact with an exponentially greater number of air molecules and dust particles. What happens to the remaining blue and yellow light? It is scattered away entirely. It is bounced out of the line of sight. Only the longest, most resilient wavelengths, the oranges and the deep, fiery reds, have the sheer power to muscle their way through the vast distance of the atmosphere and reach your eyes. The sunset is not the sun changing color. It is the Earth's atmosphere performing a spectacular, natural magic trick, filtering out every color except the most dramatic, leaving us with a final, breathtaking spectacle of cosmic subtraction. The yellow sun is a filtered sun. The red sun is a heavily filtered sun. But now, let us leave the atmosphere behind entirely. We are moving into the deep vacuum, where the air is no longer distorting our view. We are about to confront the true strangeness of our star. Look closer at the immense, blinding star filling our view. It is pure white, yes, but to an astronomer, even the word white is an oversimplification. We need to dig deeper into the physics of what makes a star shine and how its color is a direct function of its staggering surface temperature. This is where the scale of the cosmos begins to escalate, taking us from the familiar yellow of Earth's sky to the vertiginous, terrifying reality of stellar classification. Every star in the universe, from the coolest, dimmest red dwarf to the hottest, most luminous blue giant, follows a fundamental rule. A star's color is an infallible indicator of its surface temperature. This is a concept rooted in the physics of black body radiation. Imagine a piece of metal being heated in a forge. As the temperature rises, the metal first glows a dull, deep red. Heat it further, and it turns orange, then yellow. Heat it to an almost impossible temperature, and it will glow a brilliant, searing white. Heat it even hotter, and it will begin to emit a bluish-white light. The color is directly linked to the energy being radiated. The same principle applies to stars, but on a colossal scale. Astronomers classify stars using the OBAFGKM sequence, a mnemonic device often remembered with the phrase, "Oh, be a fine girl, kiss me." At the O end of the sequence, you have the most massive, hottest stars, with surface temperatures that can exceed 25,000 Kelvin. These stars radiate light that is predominantly in the blue and ultraviolet part of the spectrum. They are blue-white giants, burning through their fuel at an unimaginable rate. At the M end, you have the smallest, coolest, and longest-lived stars, the red dwarfs, with surface temperatures around 2000 Kelvin. They emit light primarily in the infrared and deep red. So, where does our Sun, the star we have been calling yellow, fit into this grand cosmic sequence? Our star is classified as a G-type main sequence star, specifically a G2V. The G places it squarely in the middle of the spectrum, just a bit cooler than the F stars and significantly hotter than the K stars. The surface temperature of our Sun, the photosphere, is approximately 5,778 Kelvin. This temperature dictates the precise color of light it emits. If you were to plot the Sun's light emission across the entire electromagnetic spectrum, a graph known as its blackbody curve, you would see that it emits light across all visible wavelengths, from violet to red. But the curve is not flat. It has a distinct peak. Where is that peak? You might assume, given the Sun's traditional nickname of a yellow dwarf, that the peak emission wavelength would fall neatly into the yellow part of the spectrum. But this is the second, and arguably stranger, deception. The Sun's peak emission wavelength is actually around 500 nanometers. If you look at the visible light spectrum, 500 nanometers corresponds not to yellow, but to the color green. That is right. The most intensely radiated single color of light coming from our star is green. I know what you are thinking now. If the Sun is truly a G-type star with a peak emission in green, why on Earth, or even in space, does it not look green? This is because of the way the human eye and the star's overall emission profile works. While the peak is in green, the Sun emits enormous amounts of light on either side of that peak, spanning the entire visible spectrum. It is not a laser emitting a single, pure green frequency. It is a massive, multi-spectrum radiator. The light curve is so broad and so balanced across the visible spectrum, emitting significant amounts of blue, green, yellow, and red, that when all those colors combine, they overwhelm our visual system. Our eyes process the total sum of all those balanced wavelengths, and the result, the additive mixture of blue, green, and red light in roughly equal proportions, is perceived as pure white. Imagine mixing paint, but with light. If you mix equal parts of red, green, and blue light, you get white. The Sun is doing precisely that, but on a scale of cosmic intensity. The slight green peak is simply not enough to visually overpower the colossal, balanced output of all the other colors. So the Sun is a G-type star. It has a peak emission in the green, and yet it appears white. This is the ultimate friction between the colossal reality of the cosmos and our limited human perception. The designation of yellow dwarf is therefore a historical misnomer, a relic of early telescopic observation, where the scattered, filtered light of the atmosphere dominated the visual data. The name stuck, even though the light is white and the peak wavelength is green. Let us now scale up. We have moved from the familiar yellow of our sky to the pure white of our star. And now, we will use our understanding of stellar color to to truly appreciate the scale of the universe. Look out into the deep field. You see a tapestry of pinpricks of light, each one a distant star. You might have been taught they are all white or yellow, but with our new understanding, you can now read the temperature and the fate of every single one of them. Do you see that intensely blue-white point of light, searingly bright? That is an O or B-type star. It is a massive star, a cosmic prodigy. Its surface temperature is scorching, perhaps 30,000 Kelvin. It is burning its nuclear fuel so fast that its life will be spectacularly short, maybe only a few million years, culminating in a cataclysmic supernova. It is a giant living life in the fast lane. Now, look at the fainter, reddish star nearby. That is an M-type star, a red dwarf. It is the opposite of the blue giant. Its surface temperature is a relatively cool 3,000 Kelvin. It is so efficient with its hydrogen fuel that it can live for trillions of years, far longer than the current age of the universe. It is the cosmic marathon runner, dim and unassuming, but virtually immortal. The color of the star is the language of its life and its destiny. And there, in the middle, a star that looks remarkably similar to our own sun, white with maybe a very subtle, almost imperceptible creamy tinge. That is another G-type star, another solar twin, with a life expectancy of 10 billion years, about 5 billion of which it has already completed. We have reached the limit of our journey into perception. We have zoomed out from the personal experience of a sunset to the universal law of black body radiation. What have we truly discovered? We have found that the universe is not obligated to conform to our immediate, filtered senses. We started with a simple question: why does the sun look yellow? And we have ended with a profound realization. The atmosphere of Earth, the very air we depend on, is an active participant in our reality. It is a lens, a filter, and a painter, scattering blue light to give us a blue sky and leaving a yellow remnant for the sun. But the moment we step outside that thin film of gas, the illusion shatters. The true sun is revealed. A brilliant, blinding white G-type star peaking in green light, a perfect, balanced radiator that powers a fragile blue world. The journey has been one of perspective. We have moved from the familiar to the vertiginous. We have learned that the color of a star is an objective, measurable truth of physics, a direct link to the colossal energy of its furnace. And this brings us to the symbolic return, the final landing back on the surface of our planet. As you watch the sun dip below the horizon tonight, painting the sky in impossible shades of orange and crimson, I want you to remember the cosmic truth. You are not looking at a yellow star. You are looking at the final, filtered, beautiful light of a white star whose blue has been stripped away by the very air you are breathing. You are seeing reality filtered through the lens of home. This leaves us with a final, open question, one that every astronomer must confront. If the most familiar object in our sky, the sun, is not what it appears to be, if our own atmosphere is capable of creating such a persistent, beautiful deception, then how many other fundamental truths of the universe are we misinterpreting simply because of the limitations of our perception or the unique conditions of our own small blue world? What other cosmic secrets are hidden, not in the distant darkness, but in the blinding, pure white light right in front of our eyes?